on to our second speaker of the session. As I mentioned, the talk will be given by Kovac-Gray, and the title is Detection of Venusian Aurora During Parker Solar Probe Encounter. And so Candace, as you may have noticed, I have a little timer going on behind my head. So I will when you start speaking.
Oh, okay.
And that will be your countdown for 12 minutes. And then it will become increasingly going from green to yellow to red as you're running, if you run over time. So.
Okay. All right. Bear with me. Can you see my screen?
Yeah.
Okay, great. So that talk title was different than I was expecting. This is not my talk. This is from Sarah Kovac, who I call my mini student, as she works with me with doing these Venus auroral observations. And her spin on it is using a solar wind model, WSA, to predict solar wind conditions throughout the heliosphere. And for this zoomed in version of it, it's looking at the solar wind conditions at Venus and trying to improve solar wind models, especially at places where we don't have solar wind instruments. And I apologize, I'm probably going to be flipping through some of these slides in a different order than she would have done, because this talk was given to the Parker Solar Probe team. So they know a lot about solar wind that gets a little bit glossed over here. So if we look at our solar system, we have the sun at the center. I have no idea if you can see my mouse. We have the sun at the center, and it is sending out plasma continuously that makes up the solar wind. As the sun rotates and it has its magnetic pole, it is dragging its magnetic field out with the plasma it's emitting. And so you get this spiral in the solar wind as this magnetic field is getting dragged out. And you'll also see that there is vertical motion to it as well as radial. And this is typically called the ballerina skirt. And when you cross this skirt, you will get magnetic field changes in polarity, whether the magnetic field is pointed up or pointed down. And when you get these nice clean spirals, you can actually see them, especially during solar minimum when the sun is not very active. You can see them in model and in spacecraft observations. So here we have a top-down view of the solar system, and this is in plasma density. At the center is the sun, and then we have the planets and spacecrafts, and we have plasma moving out. Here's that nice spiral shape. And you will see the plasma is denser in these three regions. And that's because we have faster solar wind that gets blown out, and it's going to impact slower solar wind that came out earlier. And as the sun is rotating, as this fast interacts with this slow, you get this buildup region. And you will have jumps in the magnetic field, jumps in the particle count. If it's big enough, you can get some shocks. And this is just what we call an interaction region, or if it's sustained across one solar rotation, this is a co-rotating interaction region. So if I say a SIR, it's a interacting region, or a CIR is more permanent. Okay, so why is this important? Because the solar wind affects the planets. And if we want to know what's happening at these planets, we either need spacecraft there taking data, or we need really good models if the spacecrafts aren't there. Currently, Venus does not have any spacecrafts in orbit that study the solar wind. We have Akutski, which is doing images, but not solar wind studies. So what's happening as the solar wind is moving from the sun to Mercury, Venus, Earth? That's what this science is trying to address at the Venus level. But we have this interesting opportunity where Parker Solar Probe was launched. It is a solar wind mission. It's measuring particles, fields, lots of things I can't remember off the top of my head about the solar wind, and it's doing gravity assists around Venus. So it gives us this really cool opportunity to get a massive amount of information about the solar wind around Venus. And they're doing measurements that have never been done with any craft around Venus before, any of the plasma crafts. So now we can look at some of these really high energy particles and see what's happening at Venus during these flybys. Okay, great. How are we connecting this to aurora? Because the solar wind, as it impacts a planet, excuse me while I cough on spit, as it impacts a planet, is going to have effects on its magnetic field, on its atmosphere. Venus, which doesn't have a magnetic field, is still going to be affected by this plasma. And one of the ways we see it is through auroral observations. But we don't know what is really causing these auroral observations, what kinds of particles or magnetic field changes, like what's going on. So in order to improve our solar wind models, in order to improve our understanding into the upper atmosphere of terrestrial planets with atmospheres, like in the ionosphere, we're trying to connect these two things. What's happening in the atmosphere? What's actually going on in the solar wind? And Parker is giving us that option by giving us the solar wind measurements. But at Apache Point Observatory, we're able to observe Venus and its aurora and see what's happening during this Parker Solar Probe flyby. We currently know that the Venusian aurora gets very bright around large solar storms. I'm not going to go into the background of it, but for large coronal mass ejections, these are large plasma eruptions that ignite aurora on Earth. We can see on Earth, here is a bright night glow line called the 5577 oxygen green line. It's an atomic transition. Red is the Earth, and then Doppler shifted because Venus is moving towards or away from us as it orbits. We can see that the same emission line is present on the limb of Venus. And this is observed when there is a large particle storm. Now, when we had just a stream interaction region, a co-rotating stream interaction region where it's not as big as a big plasma storm from the sun, but you still have increased magnetic fields and particles. And we see that there is a little shoulder, and we see a weak auroral emission on Venus. But then there'll be other times where there's no emission present at all. So why? And so we need these spacecraft measurements to determine what's going on with the solar wind. But what do we do if we don't have those spacecrafts? Well, we need to improve the solar wind models in order to see, hey, is anything going on when we're doing our observations of Venus? And there have been several monitoring or observing campaigns at APO with Venus. This one's going back to 2019 when Sarah started. This is our Christmas campaign where we had about 2 weeks time. We did have another observing campaign during COVID, so we lost this whole observing campaign. We did manage to get one for July and August, and then future ones for October. So what are we going to do with these observations? We're doing this monitoring project to see what are the solar wind conditions at Venus during solar minimum. What's happening with the aurora? But the problem is there are no solar wind spacecraft around Venus. So we're entirely reliant on models. But we have Parker. So what we can do is look at the solar wind model, the WSA. It's a Wang-Sheely RG model. And it predicts what the plasma environment is going to be like at Venus. But we can do a direct comparison of what the model predicts and what Parker sees to try and line things up a little better and improve our models. And during the Parker Solar Probe flyby of Venus on July 11th, we actually did, I know it's messy, there is a small shoulder to our terrestrial green line indicating there was really weak aurora on Venus. And now that we have Parker flying by, we can see, all right, what's going on? What did the model say? But what did Parker say? And looking at the WSA model, it's taking data from Stereo A, which is a spacecraft that looks at the sun, collects data from the sun, as well as we have ground-based observations on Earth. These two plots are showing the magnetic field where that polarity is. So if you imagine that ballerina skirt before, where it's the magnetic field is waving, is the polarity up, is polarity down. And when it flips, you can maybe get particle enhancements. There might be particle accelerations. And so we're just trying to see if there's a trend. But during the July 11th observation, where we think we have green line emission, we're not seeing anything happening with the models. There's no flip of the magnetic field. Looking at the solar wind speed, this doesn't really seem with the models anything to be going on. But we look at Parker, and what we see, I'm just going to jump to the next slide. This is showing the magnetic field being measured by Parker, and all of a sudden there's a jump. So it's indicating there was a magnetic flip right before we observed. We observed from APO around here, and it's difficult to tell, but there is particle enhancement in the electrons. And I don't know if I can share my screen fast enough. I have no idea. Can you see this other plot I'm bringing up? That's probably a no. Okay, great. There is a plot of higher energy protons, and that's more my realm of this, is predicting that 100 keV protons are responsible for this aurora. And Parker measured an increase exactly at that energy during this time where we think we saw auroral observations. And we really, we couldn't have done that without Parker. And these energies have never been measured around Venus before. And so now we have all this new data that we can feed into the models. And looking back at some previous observations where we think there may have been a green line detection during the 2018-19 Christmas campaign, we see where weak emission may be present. There was a dense solar wind stream that passed over, and there was a polarity crossing as well as an increase in solar wind speed. Particle counts are not here. Those are in my talks. And it's just showing more that, okay, the models are doing a good job. We can see that there are changes, but it's not quite there yet. And Parker's going to give us that extra information to tell us more about the solar wind conditions at Venus. There's an upcoming observing campaign in October that's going to be conducted from Keck for the next Parker Solar Probe flyby. So hopefully we can get observations from both Keck and Apache Point and get more accurate predictions using WSA, so that when Parker isn't there and while we wait for all our fantastic Venus missions to get there, which don't have any plasma measurements, we can know what's going on around Venus while we do all our observations from APO. And in theory, once you start improving this at Venus, now take it out to Mars, take it into Mercury, and you get a much better understanding of the inner solar wind. I am already over. So in summary, that's Sarah's talk.
All right. Thank you, Candace. What questions do you all have for Candace channeling Sarah?
Hopefully that made sense.
Any questions? So I have one, if no one else has one. Candace, and this is clearly a question that Sarah certainly can answer, and hopefully you can, but for the modeling part of it, the WSA modeling. So I guess what I'm trying to understand is how many knobs are there to turn, right? And I guess what I mean is I'm thinking a little bit about the application of this talk to some of the work that others in the ARC consortium are worrying about, active stars and, and whether or not they host exoplanets and those kinds of things. And so how much of the solar activity that's, in the model is kind of fixed, and then how much of it is tweakable? You see what I'm saying?
Exactly. Yes, yes,
Yeah.
yes. And that's more Sarah's realm. So what happens is, we'll see if we can do a crash course on this. You have the sun. If you can
Briefly.
picture the sun with sunspots, you have magnetic fields coming out. On Earth, we can see that side of the sun, and it's rotating. Those sunspots are evolving. But as one half of the sun moves out of our field of view, we're no longer monitoring it. And so what solar wind models do is they take a snapshot of the sun and then they paste it on the other side, and they just say that's the activity that's happening on the far side, when that's not realistic at all. And so what Sarah's doing is she's using this thing called an adapt model to the solar wind, where yes, you're still taking snapshots of the magnetic field on the side of the sun we can see, but now we're letting it evolve. So as it comes back around and we see a sunspot come back into view, how has it evolved? How has it changed since the last time around? And how can adapt improve these maps so it's not just static? And by adapting and improving these maps, what is that telling us on the far side of the sun, where we can't see, where there might not be instruments, like if Venus is on the far side of the sun and we're trying to do, you wouldn't do it on the far side. That's the example. It's improving it so you get a better view of the whole solar, inner solar system, solar wind, when on Earth, we actually only see one side of it. Does that make sense?
Yeah, that's great. Thank you.
Okay.